Hey there, I'm Dr. Adam Page, Principal Machine Learning Engineer at Ambiq. Today I'm going to be showcasing our real-time ECG segmentation demo running on our ultra-low power Apollo4 Blue Plus evaluation board. This is a complete end-to-end demo showcasing running real AI workloads on battery-powered edge devices. But before jumping into the live demo, let's do a quick overview.
To begin, let's quickly review some of the advantages of running health-related AI workloads on the edge. First is privacy. By running locally on the edge, we can reduce the amount of sensitive information being sent to the cloud. Second is personalization. Since the model is running locally, we can fine-tune the model specifically for the individual. Third is power. While there is increased computation running locally, we forego having to transmit all the raw data, providing significant power reduction. The fourth advantage is latency. Again, while we are performing more computation on a constrained device, we don't need to make round-trip transmissions to the cloud. And finally, by leveraging an efficient AI architecture coupled with Ambiq SPOT technology, we can enable always-on compute, ensuring we never miss a beat. The next question is why focus on heart monitoring related tasks? Let's start with a couple staggering statistics. Remote patient monitoring is valued at $14 billion and expected to reach $42 billion by 2028, with a compound annual growth rate of 20%. Second, cardiovascular diseases are the leading cause of deaths globally, responsible for 1/3 of deaths. However, about 90% of heart disease is preventable. This includes improving diet, more physical activity, monitoring stress, and getting quality sleep. By monitoring the cardiac cycle, we can keep a pulse on the health and functioning of the heart, and in tandem monitor factors impacting heart health such as stress, physical activity, and sleep patterns. With this in mind, Ambiq has created heartKIT, an open-source AI development kit that enables our developers to train and deploy real-time heart monitoring AI models onto Ambiq's family of ultra-low power SoCs. heartKIT is still in active development, but already includes a variety of datasets, tasks, and a number of pre-trained models, including ECG segmentation, which is the focus of this demo. Now, let's quickly review what ECG segmentation is and a number of potential use cases. ECG segmentation is the process of delineating an ECG signal into segments including P-wave, QRS, and T-wave. These segments represent specific phases of the cardiac cycle and help understand the health and functioning of the heart. By segmenting and identifying the various phases of the cardiac cycle, we can perform a number of downstream tasks such as capturing heart rate and heart rate variability metrics from the interbeat intervals, identifying ectopic beats that are either premature or late, identifying certain heart arrhythmias such as AFib, along with computing additional metrics such as corrected QT interval. By monitoring the cardiac cycle, we can better understand the user's health as well as draw insights into factors impacting heart health such as stress, physical activity, and sleep patterns. Having this in mind, let's walk through the flow diagram of the demo. In this setup, we are using a MAX 86150 sensor to read ECG along with two PPG channels consisting of both a red and infrared LED. These signal streams are being sampled at 200 Hz and read from the Apollo4 Blue Plus over I2C. For both streams, the signals are pre-processed by applying filters via biquad filters, along with normalization. The ECG signal is then fed into an AI segmentation model that creates a corresponding mask identifying the key cardiac regions such as P-wave, QRS, and T-wave. From the ECG signal and segmentation mask, the beats are identified and used to derive the interbeat intervals. A handful of metrics are then captured from this, including heart rate variability, and quality of signal. For the PPG stream, the channels are transformed to the frequency domain to determine the pulse rate. We also have reference algorithms to extract blood oxygenation from the two wavelength LEDs. For demo purposes, the signals, segmentation mask, and metrics are sent over BLE to our Tyleo front-end app to be shown in a configurable dashboard. The following provides high-level complexity and performance metrics of the AI segmentation model. In terms of complexity, the model only requires 7,000 parameters and 2.1 megaflops while achieving an intersection over union score of 87%. In terms of hardware performance, a single inference over a 2.5-second ECG input window takes 83 milliseconds to run and draws 6.78 milliwatts total power when running on an Apollo4 Blue Plus EVB. In terms of energy efficiency, the Apollo 4 is able to perform almost 2,000 inferences per second per watt. On average, we find the Apollo 4 Blue Plus to have 11 times better energy efficiency compared to other Cortex M4 solutions. Now let's jump into the live demo.
Here is the complete setup of our ECG segmentation demo. On the right, we have the Apollo 4 Blue Plus. In front of it, we have the sensor that's capturing both ECG and PPG. Now, once this is all powered up, we can go ahead and launch our Tyleo app. Okay, and then once we're in here, we can see that there's a device, and we can scan and see that this one's currently online. Now that we tap into this is showing a dashboard of various tiles that we've configured to show all the different metrics and data that we're capturing. So we'll go ahead and connect to the device, and this is going to start pouring in real data in real time. Okay, so we have a number of different rows. In the first row, we're showing the current heart rate, 74 beats per minute. Here we have the live ECG data that's just been pre-processed. You can also see the purple vertical lines. That is showing you the individual beats. So from those individual beats that we've captured, we're then able to calculate the interbeat interval. And from the interbeat interval, we can then calculate heart rate variability. So in this plot to the far right, we're plotting the heart rate variability Poincare, which is going to be showing the interval beats against previous ones. On the second row, we're showing the same thing, the heart rate variability, and looking at the standard deviation. And then we have, this is the actual segmentation. So this is the AI actually running, and it's identifying from the ECG signal above the actual individual P wave, the QRS, the T wave segments. So you can see the corresponding sections with the ECG signal above. It's able to capture the P wave, the QRS, and the T wave, not just simply getting the R peaks. And to the right of this, we kind of show a breakdown in a pie diagram of how much time was in the P wave, how much of it was in the QRS, how much of the T wave. So this gives a breakdown of the time for the various segments. The last row is showing you for the PPG signal. So here we're getting the pulse rate, which should coincide with the heart rate. This is based purely off of the PPG signal. Now for PPG, this particular sensor has two different LEDs. It has a red one and has an infrared at 880 nanometers. And here we can see that those signals overlap each other, and from this we're calculating the pulse rate. And we're also able to derive the blood oxygen, the SpO2, around like 96. Now right now this is showing pre-recorded data, but all of the algorithms and everything's running live. So now what we can do is we can switch this into live mode. So I'm going to pick up the sensor. I'm going to hold the sensors in my hand firmly but not too tight, and then I'm going to switch this to live. So now that it's in live mode, you can see the difference. You can actually see in real time my particular heart rate, which is around like 60 beats per minute. You can see my ECG signal, which is a bit noisier, but you can still see that it's able to identify the various segments. It's got the P wave, the QRS, the T wave. It's able to capture all of those different sections.
This is really quite powerful, as the AI segmentation model enables identifying patterns associated with specific kinds of heart conditions, such as heart attacks and AFib. This concludes our live, real-time ECG segmentation demo. If you want to learn more or get started leveraging Ambiq's heartKIT or one of our other AI development kits, please check out the links in the description below. Please be sure to also like this video and star Ambiq's heartKIT GitHub page. Thank you.